In a past video, we had talked about Fourier series and PDEs, but in this video, we're talking about Fourier transform for PDEs. Okay, and interestingly, already, I have a playlist on Fourier series. So you want to check all of that. So under the Fourier series thing, I talked about Fourier transforms, also discrete forms, and all the rest of them. So let's move on with Fourier transform for PDEs. First of all, it's important to know that the Fourier transform is a powerful mathematical tool used for solving PDEs. Of course, it's used for many other things, but we can use for solving PDEs, particularly when the problem involves an infinite domain. Of course, Fourier series covers infinite domain. So it is especially useful in cases where boundary conditions at infinity are manageable or non-existent, making it ideal for problems defined over infinite or semi-finite domains. Okay, so let's look at the concept of Fourier transform. Concept of Fourier transform. So the Fourier transform of a function f of x denoted as f cap of k is defined as f cap of k equals integral from minus infinity to infinity of that f of x e raised to minus ikx dx. Okay, so where x is the spatial variable, x is the spatial variable, k is the wave number or frequency. K is the wave number or frequency. Then we have e raised to minus ikx. E raised to minus ikx is the Fourier kernel. It's the Fourier kernel. So we also get to talk about the inverse Fourier transform. So the inverse Fourier transform is f of x. So if you want to reclaim your f of x, that will be f of x equals 1 over 2 pi integral from minus infinity to infinity of f cap of k e raised power ikx dx. Okay, so that's the inverse Fourier transform. So you may want to take things back from the transform back to the original function, and that is what is needed. So let's talk about some applications. Application to PDEs. Application to PDEs on application to PDEs on infinite domains. So when solving PDEs on infinite domains, the Fourier transform allows us to convert the differential operator in the spatial domain into algebraic terms in the frequency, which is the Fourier domain. So this transformation helps a lot. This transformation typically simplifies the problem and can make the solution more tractable. Okay, so let's go for first example. Example 1. Let's look at heat equation. Heat equation on an infinite domain. So once you see infinite domain, you should be thinking Laplace, you should be thinking Fourier transform. So consider the heat equation, partial u of x comma t partial t equals alpha partial squared u of x comma t partial x squared for minus infinity less than x less than alpha t greater than 0 with the initial condition u of x comma 0 equals f of x. So we go for step 1. So we do the Fourier transform of the heat equation. Okay, so applying the Fourier transform to both sides of the equation with respect to x. So mind you, what we are transforming is the spatial part with respect to x. So once we do that, then we have it remaining in terms of t, and then we can go on from there. So so we have this u of k comma t equals integral from minus infinity to infinity of u of x t, which is the original expression we are looking for, e raised to minus I kx dx. So we have this. So if we now take Fourier transform, okay, so taking the Fourier transform of both sides of the equation with respect to x, we get Okay, see on the left hand side, it's order one, right? If it, oh, okay, I did not write. Did I write the heat equation? Yeah. Okay, I did. Okay, yeah. So this is first order derivative and this is second order derivative. So we just apply it like that. So what do we get? We have partial t u cap k comma t equals alpha into minus ik squared u cap of k comma t. So if you apply to both sides, we have talked with our focus is on this part. So and this the left hand side remains the same, but this one is transformed. If you use this expression, okay, so it's more like you slot. So from here we just get this. So we have alpha into minus k squared into minus k all squared, right? And then we have u cap of k comma t. So that's basically applying that Laplace transform to this left hand side. This is what it gives us. So we have the alpha into the power. So ikx. So we have ik, then times that. So with this now, this is so because, or better still, we say since partial squared partial x squared in the spatial domain turns into minus k squared in the Fourier domain. Okay, so we have that partial u cap k comma t all over partial t. So the time domain is still remaining, but on the left hand side. Now you see this is I. That I, that is square root of minus one. Okay, square root of minus one all squared. So that is minus one in short. So it's more like we have minus one times k squared. So the minus comes out. So we then have minus alpha k squared u cap of k comma t. So we have that, and that is an ordinary. This is an ODE. In short, this is an ordinary differential equation in T for each Fourier mode. Okay, all right. So we go for step 2. So step 2, we can then solve the ODE, solve the ODE. So if you solve the ODE, I mean, this is pretty straightforward because, okay, let me do that. I mean, it's pretty simple. So we have partial u cap k comma t partial t equals alpha k squared u cap kt. I mean, to simplify things, that's just like du cap dt equals alpha k squared u. And we can just do, I mean, u cap, and we can just separate variables. And we have 1 over u cap du cap equals alpha minus alpha k squared dt easily. And then we can integrate. We have 1 over u cap du cap equals minus alpha k squared integral dt basically. And then this is lim absolute value of u cap equals minus alpha k squared t. This is just a straightforward thing. So we can then take exponents of both sides. So we just simply have um u cap is equal to so for the right hand side now, u cap is equal to minus u cap is e raised power minus alpha k squared t plus a constant k, if you like, or let's say constant c. So for the constant c now, so we have u cap equals e raised power c times e raised power minus alpha k squared t. So this e raised power c, now if you apply, of course, we can take it back to u cap k comma t equals e raised power c times e raised power minus alpha k squared t. But we have an initial condition, if you remember. We have an initial condition which says that when at time 0, u is f of x. Okay, so from the initial condition, from the initial condition that u of 0, u of x comma 0 equals f of x. Now, this simply implies that t is 0 and u is f of x when t is 0. So from here now, so it means that from here we just have that u of kt, we have u cap of k0, and that would just be e raised power c now. E raised power c is what we are looking for. So we have this e raised power c times t is 0. So we have e raised power minus alpha k squared 0. Okay. And all of that. So this implies that this whole thing is equal to f of x. In short, that's the idea we're trying to sell. So this is e raised power c dot e raised power 0, and that is equal to f of x. So that means that e raised power c is simply f of x. Therefore, and so u cap k comma t, which we had already as e raised power c times all that, we just simply be so now this will be since we are doing transform stuff, right? Yeah, so this will be f cap of k e raised power minus alpha k squared t. Okay, and this is the solution. But why do we have f cap k? So where f cap of k is the Fourier transform, it is the Fourier transform of the initial condition f of x. Okay, so we have that. We have solved that ODE. So we now go for step 3. So in step 3, we find the inverse Fourier. So we take it back to the domain we are coming from, right? Inverse Fourier transform. So we want to regain our f of x, because now we are still talking about f cap k. So finally, we apply the inverse Fourier transform, to find u of x comma t, which we are really looking for. And that is u of x comma t equals 1 over 2 pi integral from minus infinity to infinity, infinity domain f cap of k e raised power minus alpha k squared t e raised power I kx dk. So if we simplify all this, right, then we get, so this is finally the result we need to get. Okay, so this is the solution. This is the solution to the heat equation. So if you have an actual expression here, so we'd have been able to continue from there, but we don't know what that is, so we just leave it the way it is. This is the solution to the heat equation, expressed as a Fourier integral. as a Fourier integral, the presence of the exponential, e raised to power minus alpha k squared t shows how different frequency components, of the initial condition decay over time. Okay, so let's move on to example 2. We have yet another example while I switch over to this. So example 2. So example 2, let's look at the wave equation. Wave equation on an infinite domain. So consider the wave equation partial squared u of x comma t partial t squared equals c squared partial squared u of x comma t partial x squared for minus infinity less than x less than infinity and t positive, t greater than 0, with initial condition u of x comma 0 is f of x and partial u partial t x comma 0 is equal to g of x. Okay, so to deal with this, we go for the first step, step 1. And for step 1, usually we do the Fourier transform. So Fourier transform of the wave equation. Fourier transform of the wave equation. So taking the Fourier transform, we have two variables, x and t. Those are the two independent variables. So we focus on the spatial part. So taking the Fourier transform with respect to x. So we have u cap of k comma t equals integral from minus infinity to infinity u of x comma t e raised to minus ikx dx. Okay, that's the general Fourier transform thing. So we now apply this. So we say that the Fourier transform of the wave equation gives, so on the left hand side we have the time and its second derivative. So we have partial squared u cap of k comma t. We're now in the k domain now because of the Fourier transform. The t squared equals, now if you remember the pattern, right? If we apply Fourier transform here, it just becomes c squared for this and then minus ik of u cap, and minus ik is simply minus k squared. So generally you just have minus will always be there, the constant that was there, then the square of the k, and then the u cap. So that's a standard thing. Anytime you apply, you find the Laplace transform, the Fourier transform of the spatial part. Okay, so you have a minus, you have the constant that was there originally, k squared, and u cap generally. So that is a standard you can always bank on. So that's the Fourier transform of the wave equation. That's what that gives us. And of course, you can see already that uh, this is another ODE. So it is simply another ODE. This is another ODE in T. So we can solve it in terms of T. So we can go for step 2 now, where we solve the ODE. Step 2, solve the ODE. I mean, we're already used to solving this kind of ODEs. We just do separation of variables, and this is second order stuff. So we can, okay, I guess I need to, yeah, I need to calmly solve it so we can get it. To solve the ODE, so again, the ODE is, if you like, partial squared u cap k comma t, all right, all over partial t squared. So we can bring this over. So this is minus c squared, oh, that will be plus c squared k squared u cap k t equals 0. So because we are talking about u cap, right? The the characteristic the equation characteristic equation is, because it's second order, we can use characteristic method. So we just have like r squared plus c squared k squared, basically. So we have that to be equal to 0. And if that is the case, so we have r squared equals minus c squared k squared. That means that r alone is square root, that's plus or minus square root of minus c squared k squared. All right, so r is plus or minus ck, plus or minus ck, such. So the general solution, so we can see it's a complex thing, so we can get it in terms of cost. So the general solution is u cap of k comma t equals a k cos, because we have ck, that's ckt plus b of k sine, because we are dealing in the k domain, so c of k sine ckt. So this is the general solution. So we say where a of k and b of k are constants to be determined. So we can determine those to be determined by the initial conditions, which we have, right? It can be determined by the initial conditions. And that is what we do in step 3. So for step 3 now, we apply initial conditions. Apply initial conditions. So using the initial conditions, what do we get? The first initial condition, which says u of x comma 0 equals f of x, simply implies that u of k comma 0 is equal to f cap of k. We have that because, I mean, when t is 0, if you put t to be 0 here, t is 0, we have sine 0, so that is gone. So we just have, for this, we have cos 0, which is 1. So we just have u of kt will simply just be ak. So so it means that uk of 0 is equal to f cap of k, which corresponds with, it will just take the place of ak, basically. So this is as good as our ak. Then the second condition says that partial u partial t into x comma 0 is equal to g of x. That simply also implies that partial u partial t into k comma 0, all right, we just simply be g cap of k in the k domain. All right, so if we differentiate that thing and put 0, so we are only going to have, so even the b itself will be gone. But so I'm feeling lazy right now. Okay, I'll just do it roughly here, right? If we differentiate this, right, and we get partial u cap partial t, so we just have, okay, I mean, okay, let me leave you to fill that in, because we've done this a lot of times. to, already get used to this. So I just save time. So from all this, what do we get? So this, from this, we find, so normally we differentiate that and substitute 0 for t, and whatever we get as partial u partial t. So we find that u cap of kt is f cap of k cos ct plus g cap of k all over ic sine ct. So that's what we get by applying those conditions. And with that, now we can go for the final step. So we go for the final step, that's step 4. So in step 4, we have the inverse Fourier transform. Inverse Fourier transform. So for the inverse Fourier transform, that's the final step. So finally, applying the inverse Fourier transform, we get u of x comma t, and that is equal to 1 over 2 pi integral from minus infinity to infinity of f cap of k cos ct plus g cap of k all over ic sine ct into e raised power ikx dk. So this is like what we finally get when we do the inverse Fourier transform. So now this is the general solution to the wave equation. Yeah, in conclusion, right, the Fourier transform method provides an elegant way to solve PDEs, particularly for problems over infinite domains. By transforming the PDE into an algebraic equation in the Fourier domain, we can solve for the Fourier coefficients and then inverse transform to obtain the solution in the original spatial domain, just like we've been doing. This approach is widely used in problems involving heat conduction, wave propagation, and diffusion in infinite or semi-finite domains. All right, so I have a Python code for this so we can visualize what's really happening here. So you can see we declare the efficient coefficient of heat conductivity. That's our alpha, or if you call it c squared, whatever. So we have the boundary, left boundary of the domain minus 10, right boundary is 10, maximum time is 5. You can change that. Endpoint number of spatial points is 1024. You can change it. End time steps 100. Then we have dx, that's maximum x minus minimum x divided by the number of points. That's the spatial step size. And the t, that's maximum time divided by number of time steps. And then, you have the spatial grid defined here. Then the initial condition, which is minus x squared, like we have there. If we use minus x squared in that case. And then you also define the heat equation itself. So that's f of k exponents minus alpha, like that, under the integral, and then we use the frequency values for Fourier space, and we just run this and we get what that should give us. So you see, like, of course, just as usual, like it starts from at time 0, right? The heat is at the highest and it keeps dropping until it goes to until the time is over. Basically, that's what is happening here. Okay, all right. So that's what the Python code looks like. In this case, I think we have a couple of questions we can practice with. Let me see if I can find one or two. Yep. Okay. So practice now. Practice. Solve the following. Once you see infinite domain, you already know you are using Fourier transform. Solve the following. I'll just say partial squared u. In fact, let me make it in another form, which you already know. So uxx, utt rather, that's partial squared u partial t squared utt equals c squared uxx. It's the same thing like we've always done. So minus infinity less than x less than infinity. This is infinite domain. That automatically tells you you're using Fourier transform. And then you have initial conditions of u of x comma 0 is sine x, and partial u partial t x comma 0 is 0. So it's the same procedure, except that now the conditions are different. Let me find a second one. Okay, just need one more. Okay, let me go for this. So let's do a wave equation. U t t again minus u xx equals 0, being a wave equation on the infinite domain, minus x less than infinity, t greater than 0, and we have u of x comma 0 is equal to e raised to power minus x squared, and partial u partial t of x comma 0 is 0. Okay, try this too. Let me see your answers in the comment section, either on Facebook or on YouTube. And of course, let me also know if there's a topic you'd like me to teach, or a problem you'd like me to solve, and how helpful these videos have been for you. Feel free to let me know. And if you have subscribed, thank you. If you haven't subscribed, please go ahead and subscribe, and be sure to click the notification bell so you can always get alerted each time a new video is released. Then don't forget to share, like, and share with others so that more people can have access to this great content we have going on here. So, like, come your way again. Keep doing maths right. Bye.